Today we will start with the next topic, that is air standard cycles and their analysis. This topic is for the comparison of internal combustion engine cycles. The main purpose of this topic is to analyze the internal combustion engine cycle, Otto cycle, diesel cycle, dual cycle. So the first we will start with the introduction. The operating cycle of an internal combustion engine can be broken down into sequence. There are total 5 processes. The first process is your intake, where air fuel mixture will come into the cylinder. Then there is a compression. We will compress air fuel mixture. Then after compression, the combustion will take place. Then the piston will move down, high pressure gases will move the piston, and we have expansion process, that is also power stroke. And then we have the exhaust, where we will reject the burned gases, and this whole process will repeat again. These 5 steps will be repeat again. So this 5 step, if there is some process which will repeat itself, it is called a cycle. So if these 5 steps will repeat, it is called a cycle. Okay, but the internal combustion engine does not operate on a thermodynamic cycle, as it involves an open system. But जो whatever actual engine we have, they operate in actual environment, and they operate in open system. Like air fuel mixture will come from environment, and after burning and combustion, the air fuel mixture, after combustion, it will convert into some products, and that will is rejected to environment, and there is also some loss from the internal combustion engine. So it means the working fluid enters the system at one set of conditions and leaves at another. The working fluid is air and fuel. So at the inlet, temperature is different, pressure is different, composition of air fuel mixture is different, chemical composition is different, and at the outlet, while at the outlet, the temperature is higher, as you can see in internal combustion engine exhaust, tailpipe temperature is higher, pressure is higher, chemical composition is different. Okay, so all that conditions, when the air fuel mixture after burning will leave at the engine exhaust, is different. So it means we are engine is working on open system, open cycle. However, it is often possible to analyze the open cycle as though it were a closed one, by imagining one or more processes that would bring the working fluid at the existing conditions back to conditions of starting point. But because it is very difficult to analyze open cycle, it is not possible. It is not possible to analyze the open cycle, because the things will be very complex. So we will treat internal combustion engine as a closed cycle, but the condition is that a working fluid at the exit condition must be at same point. Because if you there is a cycle, okay, if there is a cycle, the inlet conditions will be same, inlet condition will be same, and when the gas, you can say working fluid, will be outlet, at outlet it should be at same condition as inlet. Okay, then the cycle will work. Okay, so the condition is working fluid at the exit conditions should have same conditions as starting point. The accurate analysis of internal combustion engine process is very complicated. So what we do, we will simplify the things. In order to understand them, it is advantageous to analyze the performance of an idealized closed cycle that closely approximates the real cycle. One such approach is air standard cycle, so which is based on the following assumptions. So what we will do, we will simplify the things. We will won't consider any fuel. We will consider that only working fluid is air throughout the engine cycle operation. We assume air is the working fluid. Okay, we won't take the fuel because otherwise the things would be very complex. So we simplify. The assumptions are here. The working medium is assumed to be perfect gas and follow relation PV is equal to mRT. Okay, or if you divide, if you take this V on this side, then P is equal to density R and T. Okay, whereas is universal gas constant, T is temperature in Kelvin. There is no change in mass of working fluid. As you know, the mass conservation principle will be applied, and there is a more mass change in the working fluid medium. Okay, mass will be constant throughout the cycle. Throughout the cycle, the mass would be same. All the processes that constitute the cycle are reversible. Okay, heat is assumed to be supplied from a constant high temperature source and not from a chemical reaction during the cycle. It means we assume that there is no chemical reaction taking place. We assume that heat is supplied from a constant high temperature source and not from a chemical reaction during the cycle. Some heat is assumed to be rejected to a constant low temperature sink during the cycle. Uh, One thing to remember, that whenever there is a cycle, it operates between two temperature limits, high temperature limit and low temperature sink. High temperature source and low temperature sink. You can take here this in diagram, you can see here. So you can see here in this diagram below, this diagram, working principle of a Carnot engine. You can see here, this is a perfectly insulated wall. Okay, this is perfectly insulated wall. This is your piston. This is perfect insulator come perfect conductor. So we have, one is high temperature source at T3 higher temperature, another is T1 low temperature sink. So what we do, we first consider that this boundary is totally insulated. Okay, there is no heat loss from this boundary. Second, that this is high temperature source and low temperature source. These are used to this is used to transfer the heat to the this system, and this is used to take heat from the system. Okay, so we don't consider any chemical reactions here. We will consider that only there is a high temperature source and not from chemical reactions, and there is a low temperature sink. Okay, so we don't consider any chemical reactions. It is assumed that there are no heat losses from the system to surrounding, as we had discussed. The working medium has constant specific heats throughout the cycle. Because we consider air as a working fluid, with the temperature these three parameters will change. Cp will change, Cv will change, gamma, and these parameters will change. But we to simplify the calculations, we assume that the constant specific heats throughout the cycle to simplify the things. The physical constant Cp, Cv, gamma and m of the working fluid are the same as those of air standard atmospheric conditions. For example, in SI units, the value of Cp is 1.005 kilojoule per kilogram Kelvin. What is Cp? It is a heat addition at specific heat at constant pressure, and Cv is a specific heat at constant volume. M is 29 kilogram per kilomole. This is for air. If you consider, if you take the air is a mixture of gases, oxygen, nitrogen, hydrogen, carbon monoxide. Number of gases are here in the air. So take the average mass of the air, that is 29. Okay, gamma is 1.4. Ratio of Cp by Cv is called gamma, and it is 1.4. The ratio of Cp by Cv. Due to these assumptions, the analysis become very simplified, and results do not agree with those of actual engine. But it is easy to solve the equations. Work output, peak pressure, peak temperature and thermal efficiency based on air standard cycles will be maximum that can be attained, and will differ considerably from those of actual engines. It is often used mainly because of the simplicity in generating approximate answers. Okay, and to avoid complicated, you can say complicated calculations. Okay, in this chapter we will review the various cycles and also derive the equations for work output, mean effective pressure, efficiency, Also comparison will be made between Otto cycle, dual cycle and diesel cycle. Okay, this is up to here the introduction. In the next class we will start with the Carnot cycle. Okay.